Welcome back to this Tezos X-Plained episode. Today's topic is data availability layer of Tezos, and we are super happy to welcome Arthur Bretman, co-founder of Tezos, to talk about this topic.
Thank you. I'm super happy to be talking to you.
Excellent. So, as a baker, I started my baker, the latest version, and it tells me I won't run if I don't have a DAL node running on the same infrastructure.
That's right.
What is DAL? Why I should care and actually run a DAL node?
Well, we need to go back a little bit at first on like what is data availability in the first place? Why do we have it? I think it's one of the more poorly named aspects of blockchains, and as a result of being poorly named, it's poorly understood. What does it mean for the data to be available? Available when? To whom? I think a better term for it that was proposed by I think Dan Feast from the Ethereum ecosystem is proof of publication or data publication. And the idea is that what it shows, it's a way to prove that at some point the data was disseminated, and then anyone who would listen at this point was able to hear it. The reason it matters if you build a blockchain, let's go back to building a very, very simple payment system. The first naive way you can do this is say, oh, I'll just write a check and I'll have a digital signature. The problem if you do that is you could give the same signature to two different people, and then you have a double spending problem. So you'll say, very well, I'll have a timestamping service, right? And so I'll give you a transaction, and I'll give someone else a transaction. Oh, they're timestamped, right? Even though there's a timestamp that now tells us which transaction came before which, and a timestamp can be trusted. Before you accept my transaction, you want to make sure that I have never published any transaction that would conflict with that one with a lower timestamp. And that is a proof of publication. And so the way that a blockchain achieves that is we'll store everything on a blockchain. So every node on the blockchain will just store every transaction forever. The downside with this is that every node has to do all the work. And the idea of the data availability layer is that we're going to spread this load across all the bakers. So instead of every baker having all the information, bakers can download little shards of information in proportion to how big they are. So bakers on Tezos are already running a data availability layer, the Tezos blockchain. The Tezos blockchain is a data availability layer, but now they're running another one on top of that. But unlike the data availability layer of the L1, the existing one, where it doesn't matter if you are a huge baker or a small baker, you've had to download all the same information. In here, how much information you need to download is proportional to your stake. So it's a bigger load for very large bakers and a much smaller load for small bakers.
Okay, so if I understand correctly, in let's say the first version of blockchains, the one before 2020, let's say,
yeah,
every validators, every node, we are downloading everything.
That's right.
Well, actually, with this more efficient publication layer, we have a smarter way to distribute data and still attesting that it's univocally published for everyone.
That's right. But the trick is, for you to benefit from such a layer, you need to have a rollup. Because if you're still in a mode where every node executes every transaction, then it wouldn't work, because then you need all the data. But now, once you start outsourcing execution to a rollup node, for example, whether it's an optimistic rollup or a validity rollup, it becomes purely about the data availability, and then you can start sharding it. So that's why, on Tezos, the order went first, developing the ability to have smart rollups. And then now that we have smart rollups like Healing, increasing their capacity by adopting a sharded data availability layer. And that's part of scaling Tezos.
Oh, yes, because in this new layer, we have this very good property that if you add more nodes, you get more bandwidth. Is that like BitTorrent probably has also this property in some sense?
It can be that. So there are parameters that you need to choose in a system. The thing is, you can't really count how many nodes you have in a network. And people will say, oh, you can count the bakers, but you don't really know what the actual capacity is. So rather, the way that the DAL works is that you set a bandwidth target. How many megabytes per second do we want to prove that have been published? So you choose this bandwidth, and then that bandwidth is going to be spread between people who stake. So the bigger your stake, the more bandwidth you're going to have to provide. We're still talking about very low numbers. Even for very large bakers, we're talking about numbers that they could achieve with a home connection, right? So these are very, very small numbers. But you have to do it this way. And in some sense, you have an equilibrium that happens that's really interesting, which is if somehow people found that, oh no, the demands for bandwidth are so high, I will stake less because I can't pay that much bandwidth. Then what would happen is you would have less staking, a little more issuance, and that would pay for the bandwidth. So in some sense, the system will adjust. Like the issuance of the system will adjust to pay for the bandwidth. This is a bit of a theoretical consideration because the numbers we're talking about are just so low.
Yes.
That it's, the cost doesn't really register. But in theory, it matters. If you want in the future to move to a system where you would have, maybe tens of gigabytes attested per second and so on and so forth, then, okay, you need a real budget. The interesting thing as well is that it actually pushes for decentralization, because adding more nodes to the system, adding more bandwidth to the system does mean that you still would have to use governance to decide to increase the bandwidth that you want to allocate to the DAL.
I think on the DAL, there are some misconceptions that are still running inside the Tezos community.
Yeah.
First one, people really think that the DAL is a storage system, where actually it's really about bandwidth, making sure it's published. So you already explained that.
I think it's very, very common to imagine it as a storage system and say, oh, should we store NFTs there and so on and so forth. No, it's proof of publication. You want to prove that this data was published. And why do we care that it was published? Because if it weren't valid, then someone would have a chance to say something in an optimistic rollup. And if you want to guarantee that it's available later, I don't think it's something worth sweating over. Like, you could try to create incentives, that's very tough. All you need is one honest archivist. Like, you need to have one person who's willing to actually record it. And because you have the proof of publication, as long as this person is online, they can archive it. The cost needs to be still moderate, but having access in the future is still quite feasible, but it's also not that important in a sense. Like, what really matters is that you want to preserve your state, and you want to have confidence that you arrived at this state in a valid way. But you don't necessarily know to be able to recreate it. It's a nice property to have. It's not a fundamental property to have. But what was the second point?
Second point is this idea that the DAL would be a new product. Just like Celestia, we would offer this data publication service to the rest of the industry of whatever. Well, actually, I think for Tezos, it's another strategy that we're following.
It's possible. Like, we could offer the DAL could be used by outside parties. That's a strategy that has been, followed by Celestia. I don't think there's a giant amount of demand out there for people who want to have externalized data availability. I also think that it doesn't work as well. So what Celestia does is so-called sovereign rollup. And the concept of a sovereign rollup is that it has data availability, but it doesn't run on top of a blockchain. It doesn't have a bridge. But, a sovereign rollup is more of an orphan rollup. It's a rollup that lacks the fundamental ability of rollups, which is to talk to each other. The fact that you can run two rollups on a chain and can safely talk to each other, that's wonderful. And you lose that. So it's not that great. And the second thing is, when you use a data availability rollup for a rollup built on Tezos, you have this very tight coupling. In a sense, as long as the Tezos chain is secure, you're going to have your data availability. The chain will fork for it if there's a problem, or the chain will alt if people detect that data is not available. So you have these very, very strong guarantees. Whereas if you externalize it, in some sense, all you're getting is a notarized proof that this thing has been stored somewhere. You don't really have very, 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 very good guarantees. So for me, it's less appealing as a product, even though there's been a lot of marketing for people wanting to sell this type of things as a product. I think it has better fit as a support for Tezos rollups, which is not to say that, if people want to use externally the Tezos DAL, they can do that, but it's not a primary goal.
And nonetheless, the DAL will bring actual value for users. I've read recently that something like 95% of the transaction cost in Rollups on Ethereum actually publication costs.
Yeah.
So if you're able to put them in efficient cost model, it's great. And another point is also what I really like with Tezos is this idea that we have a very clear trusted base.
Mm-hmm.
We don't need to change it to extend it to use external parties. No, we have something very very neat and. Yeah,
it's self-contained. But the thing about Ethereum is that they've been planning their own DAL for a long time. Mm-hmm. It's gone by different names. I think the latest one, and they call it, was danksharding. But they're still working on it. And what they've done in the meantime as a stopgap is a thing that they call blob. So the idea of a blob is that it's the same old data availability where everyone downloads the same data. Mm-hmm. However, they decided that they would add data to their blocks that was not executable. So in some sense, they were like, okay, we know that this data is not executable. At least it's executable by rollup nodes, but not by our validators. And therefore, we don't feel it's going to add too much load to the validator, so we can, charge access to the space for cheaper. And so that removes some of the congestion for the rollups on the Ethereum ecosystem, but it's still quite expensive. DAL is pretty much a future-proof solution in that respect.
So if DAL is not a product, what indirect impact it will have on Tezos users, and especially in the Tezos X canonical rollups that we are talking about?
Right. So for rollups, it means that rollups have a guarantee, in some sense, a future-proof guarantees that they can put a lot of transactions out on a Tezos blockchain without the costs. So, it's future-proofing in terms of the volume of transactions across rollups. And particularly for Tezos X, which aims to be a high throughput rollup, it can give a lot of bandwidth for Tezos X to put out all the transactions that it needs to put. If you want to have 1 million transactions per second on Tezos X, then you require a lot of that availability.
So referring to what you said before, so it means that in the case of the canonical rollup,
yes,
actually the canonical rollup will download everything, mostly coming from the DAL, or?
Yeah, that's right. So I think it goes in the spirit of the canonical rollup. If you look at the rollups initially, one of the beautiful aspects is to say, look, you can have these rollups run in parallel. So different people can run them. And then with the DAL and the data that they can use can be sharded. The idea of the canonical rollup is to say, look, all of that is true. But that being said, there's one big gain that you can make is a move from the honest majority assumption to the single honest party assumption. And the single honest party assumption being so much weaker, we can afford to raise the requirement for that thing. And so in the same way that you have very high hardware requirement potentially for running something in the future like Tezos X, you're moving from, maybe a Raspberry Pi that costs you like $30 to maybe a machine that will cost you like $10,000. It's still quite reasonable in the realm of like the type of IT operation that people have. It's reasonable for a system that can run millions of transactions. The same goes for bandwidth, right? So if you have Tezos X, it does need to have the entire bandwidth, like being able to take in all the data availability. The bakers themselves, they just need to have one part of it. They prove that their part was published, and so they can prove that to the whole network. But yes, the person or the persons, it could be more than one, running Tezos X node would have to download everything. So it does put some temper on how much you can demand there. But you still have the possibility of scaling horizontally with many rollups as well.
What I really like with Tezos DAL, in comparison with, let's say, the data availability committee that are far more centralized, actually running a verifier for the canonical rollup. It's completely open, and of course you need to pay for the machine.
Yeah.
But if you believe you are more honest than others, actually you do have access to the data, and nobody will censor this data if the DAL is running correctly.
Yeah.
And I think it's a key to really show that we are really taking decentralization seriously.
And again, I think you can scale things progressively. But if you have a system that's making millions and millions of transactions, maybe billions per day, and surely within that ecosystem there's going to be one honest person who can spring for one big computer and a bit of bandwidth and do that. But also, like with the current DAL that's being launched, I think the bandwidth is only 500 kilobytes per second, and that's shared across all the bakers, right? So it's clearly something that a single rollup node can afford, and it's clearly something that spread over the bakers is very minimal.
Yeah, to make sure the system is running well, but actually it can scale to megabytes per second and even gigabytes. There is no other limits than the actual network bandwidth.
So my rule of thumb is I like to compress. I think you can compress with aggregated signature or transaction down to around 12 bytes is quite doable. So if you want a million transactions per second at 12 bytes, that's 12 million bytes per second. Multiplied by 8, that's 100 megabit per second.
Yes.
And like a lot of people now have gigabit connection at home. So even even for Tezos X, the giant rollup that it can do 1 million transactions per second, we're still talking about like buying like perhaps something like more stable than this, but you get the point. We're talking about hundreds of dollars a month in bandwidth expense for the end vision of this thing.
I know it's quite technical, Arthur, to enter into all the details of how that works, but still I think we can explain the main ideas, main concepts that make all this magic happening.
Yeah, so the main ingredient of data availability, the sharded data availability, the way this like what makes it work, is a thing called error correcting code. And the idea of error correcting code is that You take a big piece of data, and then you cut it into many pieces. But the idea is that if you have enough of these pieces, not all of them, just enough, you'll be able to reconstruct the whole thing. What it lets you do, for example, is say, okay, I'm going to take this data. Maybe I have a megabyte of data. I'm going to make 2 megabytes out of it, but I'll have 100 pieces. And as long as I have 50 out of those 100 pieces, I can reconstruct the whole thing. What's great is that in a model of honest majority, for example, with Bakers, you could distribute those pieces. And as long as you have an honest majority, you'll be able to reconstruct it. Because if you were just to naively cut the data and give it to everyone else, all it takes is one person to say, oh yeah, I have the data. And now you're missing a critical piece of information. Yeah. So those are error correcting code. And an analogy that I like to give, and it's a deeper analogy than it sounds, is like it's a bit like a hologram, right? If you take a hologram and you cut it into pieces, then every little piece has a representation of the hologram. And error correcting code are very similar. In fact, at a deeper mathematical level, holograms represent the Fourier transform of the data, and you also use for error correcting code. So the Fourier transform essentially takes something that has these localized features. So you have this part here, and then spreads them everywhere. So that even if you get little pieces, you have some information about the whole. That's really what makes those systems tick and what allows sharding data availability.
Yeah, it reminds me of the CD-ROM where you scratch it a little and actually continues to work, and it's the magic of error.
Exactly. Yeah.
And it's the same. It's really creating reliability on a communication channel, and again, mathematics at work.
Absolutely.
Some time ago, people were talking a lot about sharding, not only data distribution, but also execution. And it looks like this idea has not the same interest today.
People have defined sharded execution as many different things. I think a lot of the proponents of the early ideas were in the Ethereum ecosystem, where they were talking about, well, we need to execute these transactions. Maybe we'll have some people execute some transactions, other people execute all transactions, and sort of reconcile this. And these ideas haven't really panned out that well. What people have done instead, and it's sometimes called sharded execution, is either parallel execution on a CPU. So you're not really sharding across your validator base, but you're saying, look, every CPU today has multiple cores. GPUs have even more cores. So there's a lot of parallelism inherent in systems. Maybe we can have, our transactions explicitly tell us when they don't affect each other and then run them in parallel. So that's a common technique that's used in Solana, that's used in a few others. I think that you can actually reach very, very high throughputs without even needing that, as long as you parallelize signature verification, which is the most expensive one. But if you think about it, if you want to do 1 million transactions per second, assume that you have enough parallelism to check all your signatures. The next thing you need to do is move 1 million bits, in a database that's just not that long. You can do that with a single CPU. And then, of course, rollups. So horizontal scaling with rollups. That is a form of sharding, but it comes with a cost that the interaction between rollups is a bit cumbersome. It can take weeks for optimistic rollup. If you want to have very, very strong proof guarantees, it can take tens of seconds for systems with zero knowledge proofs. You're not going to have this very nice atomicity and composability. So while I think it's interesting, I would put it more into the future because you can get a lot of mileage out of this modulitic scaling where you have a single layer 2 with a lot of computing power. It doesn't sound elegant, and it's extremely pragmatic. But interestingly, if you really, really wanted to say, no, I really want to shard execution, execution itself. Well, what you could do is you can you take a program and then you run out the trace of the program. So you're going to execute a program step by step and take every single step one at a time. And the problem is if I give this to different people, if I say you're going to execute the first part of the program and then you're going to execute the second part and so on and so forth, questions of parallelism aside, I still have to trust that every single person did their job right. But it turns out that you can actually take a trace of a program, this sequence of steps, and turn that into a hologram and do a prior error correcting codes on that. And if you do that, you actually get the construction first starts, which are a form of zero knowledge proof of for executing programs. So in fact, there are some connections between the techniques used for data availability sampling or sharded data availability and for creating zero knowledge proofs, which I think is a very nice. It's more than a coincidence, but it's a very nice thing to contemplate.
So I think we have covered a lot of topics related to the DAL. Maybe you do have a final remark, Arthur?
Yeah, so over the years, I think like some people have made a lot out of the trilemmas, which was proposed by Vitalik between decentralization, security, and throughput. And the answer to that essentially is rollups and adaptability desampling. If you have those two things, then you basically have all the properties. I'm not just talking about the ability of like putting more compute power behind something like Tezos X. I'm just talking generally, you can scale with the number of nodes that you have in a network. We're about to achieve that on Tezos, and that's very exciting.
I agree.